I will show you some questions from DSC last year, 2020 paper, which is going to talk about two variable regression model, which had multiple linear regression model, which had some aspects of dummy variables to it. So we would be seeing some questions on those also. Now, ideally, the book that I suggest for econometrics would be Gujarati, Damodar Gujarati. And the chapters that you're supposed to do would be from chapter 1 to 13. These are the major chapters that you have to focus on. All right, so let's start with this then. Now, you know, especially people who are from non-economics background have this question as to what is econometrics in the first place. So econometrics is economic measurement. Now, you know, this is the break of the word econometrics, economic measurement. But what is that exactly? So ideally, supposedly, I understand, like for example, let me talk about agricultural economics. And let's say that I understand that, you know, yield is a function of, let's say, rainfall. The yield of in the agricultural sector is a function of rainfall. And let's say it's also a function of fertilizers used. Let's say it's also a function of number of labors on your land and the amount of land, so area of land. So, you know, my yield is a function of too many variables. Now, I want to understand how much is rainfall affecting agricultural yield? How much is fertilizers affecting agricultural yield? Does increasing the number of labor actually increase the agricultural yield or not? So the way that I would be defining this mathematically would become an econometrics problem. When I would be saying that, you know what, if there is more rainfall, it would be a better yield. If more fertilizers are used, it would be more yield. If the number of labors are increased, it would be more yield. So when I am going to define that relationship mathematically, that is going to be part of econometrics. So this is where I already have an economic phenomena in my mind, but now I am using that economic phenomena to tell things mathematically. I'm able to tell you that, you know what, when you increase labor by 1 unit, your yield increases by so and so units. When I'm able to give you that, that is econometrics. So econometrics is basically a tool which helps you to give, you know, mathematical analysis to any economic phenomena. Let's deep dive into it. Now, a lot of people ask, especially, you know, when we talk about statisticians, when we talk, now statistics and econometrics are, by the way, interlinked, but a lot of people ask, why do we need econometrics as a separate discipline? Why can't you just tell me that there is this, you know, correlationship between yield and rainfall? Why don't you just tell me that there is a correlationship between yield and labors? Well, yes, there is this correlationship that exists and we agree. But what if I want to have one of the variable as a dependent variable, and this dependent variable depends on a lot of independent variables, and I want to define a one-way relationship? What if I just want to tell what you know, when I talk about correlation, it's a two-way relationship, right? But what if I want to talk specifically about a one-way relationship? What if I want to tell what happens to my happiness when my pocket money increases? That is what econometrics will help me do. So ideally, economic theories are making statements for you. Economic theory, for example, macroeconomics, tells me that, you know, there is an inverse relationship between inflation and unemployment, and that is given by the Phillips curve. For example, macroeconomic theory tells me that there is a relationship between unemployment and GDP. There is a relationship between inflation and unemployment. I know what is an Okun's law. I know what is a Phillips curve. But what if I have to tell this mathematically? What if I ask you that when, as a policymaker, when I increase inflation by 1%, by how much will my unemployment decrease? That is something where econometrics is going to come into play. Similarly, for microeconomics, I understand when a firm will increase the price, the quantity demanded will decrease. When the price will increase, the quantity supplied will increase. But what happens if I have to show that relationship mathematically? Theory will not give you any numerical number. That is something which is given by econometrics. So now we'll talk about the methodology of econometrics. Broadly speaking, econometrics is based on these 8 main steps, lines. You have an economic theory. I understand that there is a negative relationship between unemployment and inflation. You have a mathematical model for that theory. So for example, I understand that unemployment is a function of inflation and this is a negative function. I have a mathematical model with me. I'm going to go ahead and obtain a econometric model for that. So I'm going to write this, that unemployment is beta naught plus beta 1 inflation. I'm going to convert this mathematical model into an econometric model. I'm going to collect the data. So I will have data that is going to tell me that, this is the unemployment, and correspondingly, these are the values of the inflation for those unemployments. After I obtain the data, I'm going to estimate the parameters. So I know that my model looks something like this. I know the values of these. Based on this data, I will show you how we will calculate it. But based on these data, I will calculate beta naught and beta 1 for you. Supposedly, beta naught comes down to 400. Beta 1 comes down to minus 0.9. I will make down that econometric model saying U is equal to 400 minus 0.9 inflation. I get my model. Once I get these parameters in place, once I have these beta naughts and beta 1, I'm going to test whether these are statistically significant or not. We'll do all this, don't worry, but I'm just giving you the steps for it for now. So what do I mean by statistical significance? By statistical significance, I am saying that I'm going to run a hypothesis testing on it at whatever confidence interval you want to run it at. So maybe you want to keep your alpha at 5%. Maybe you want to keep your alpha at 1%. Maybe you want to keep your alpha at 10%, whatever you want to do there. So depending on what alpha you have, you're going to go ahead and pick up these values. And once you have done that, you're going to do a forecasting. So for example, I get my beta naught and beta 1 significant. The moment I get them significant, this implies that there is in fact a relationship between unemployment and inflation. So once I get that in place, once I have this relationship in place, then I'm going to go ahead and I'm going to predict the values. What do I mean by predicting the values? By predicting the values, I mean that now when somebody will ask me as a, if somebody is a policymaker, some government comes to me and they ask me that, what, I want to keep inflation at 4%. What do you think will be the unemployment level? Then I will go ahead and say that, well, I have this model in place. And according to this model, if I place 0.04 here, when your inflation is 4%, I'm going to give you a value of the unemployment. So this is where you're going to go ahead and predict your model. Once you do that, you're going to use the model for policy purpose. Using the model for policy purpose is what I just mentioned. Whatever you want to give me, whatever value you want to give me, accordingly, I will give you this values. So, I will be able to tell you that, if you want to control unemployment at, let's say, 200, or let's say, whatever, if you want to control unemployment in terms of percentage at 5%, then correspondingly your inflation should be so and so. So I will be able to give you the values accordingly. So majorly, any econometric policy, any econometric model goes through all these 8 steps. You get the data, you frame an econometric model, you test its significance. Once it is significant and you know that the model is correct, you go ahead and you run that model. So once we are done with that, the next part of this econometrics is the statement of theory or hypothesis. Now, what is hypothesis for that matter? Hypothesis is what you want to go and test. So for example, in my Phillips curve, my hypothesis will be that there is, okay, so I'm going to go ahead and talk about 2 kinds of hypothesis right here. I'm going to talk about something which is null, and I'm going to talk about something which is alternative. Do not worry, I'm going to take this back in chapter 2. This is just the beginning. So one is going to be my null hypothesis, and the other is going to be my alternative hypothesis. As null hypothesis, you are always going to assume that there is no relationship between 2 variables. As an alternative hypothesis, you're going to go ahead and write the relationship that you want to prove. At the end of the day, your aim is to have this you reject this null in favor of alternative. So let's see how that happens. I'll do it for Phillips curve first. So Phillips curve suggests, I'm taking the basic Phillips curve, I'm not taking augmented Phillips curve. If you're not clear with the concept of Phillips curve, do not worry. We would be doing that as part of macroeconomics. So, I'm going to state that, so I know that the Phillips curve suggests that there is a negative relationship between unemployment and inflation. Now, this is my statement that the Phillips curve has given me. Let's write down the null hypothesis for this. The null hypothesis will be there is no relationship between the unemployment rate and inflation. So my null hypothesis is suggesting that there is no relationship that exists between unemployment rate and inflation rate. Now I'm going to write my alternative hypothesis. So my alternative hypothesis will be that there is a significant relationship. I'll tell you different ways of writing this also. So there is a significant relationship between unemployment rate and inflation. Now, usually, if you do not know the relationship side or the sign of the relationship, then you will write that there is a relationship between unemployment and inflation as the alternative hypothesis. But if you know the sign In my case, I know that this is the negative relationship that we have. So if you know what the sign is, then your alternative hypothesis is directly going to write there is a negative relationship between unemployment rate and inflation. And you know what I want to do is I want to try and reject my null in favor of alternative. We'll do this in detail, don't worry. Similarly, let's take some more examples. So for example, let's say that I have my null hypothesis as, you know, supposedly I want to talk about the demand theory. The demand theory tells me, the law of demand tells me that there is a negative relationship between price and quantity demanded. So I make my null hypothesis as this. There is no relationship between price and quantity demanded. And I write my alternative hypothesis as there is a negative relationship between price and quantity demanded. So usually, whenever we go towards econometric theory, the first thing that you should have is a statement in mind. What do you want to prove? What relationship are you looking for? Why do you want to run this model? And the reason you want to run this model, that's the statement of your hypothesis. So my statement is this: I want to prove that there is a negative relationship. I want to quantify this negative relationship. In this case, I want to quantify this relationship. So let's see. Keynes stated the following. He stated, and you know, because at that time that was the kind of language that they would use. So the fundamental psychological law is that men are disposed as a rule and on average to increase their consumption as their income increases, but not as much as increase in their income. So ideally, in simple terms, he suggested that as your income increases, your consumption increases, which means we know from macroeconomics that my marginal propensity to consume is between 0 and 1. It's greater than 0 because change in consumption due to change in income is positive. It's less than 1 because consumption does not increase exactly as much as income. Again, something to be done as part of macroeconomics. But you should know this, right? So in simple terms, this becomes my statement of hypothesis, that there is a relationship between income and consumption and a positive relationship. As income is increasing, consumption is also increasing. And my null would be that there is no relationship at all. So the next thing, as I was suggesting, is specification of the mathematical model of consumption. So now I'm going to take the same example, and I know that consumption and income have some positive relationship. For the simplest function that I want to talk about, I'm going to take a linear relationship. This is a linear relationship. I will shortly discuss what is non-linear and linear in detail. But just by looking at it, I know that this is a linear relationship. If supposedly my equation looks like this, beta naught plus beta 1x. Some books would write it like this. Some books would write it like beta 1 plus beta 2x. Different ways of writing the same equation. Now, this, we are going to go ahead and discuss this, would be my intercept term. This would be my slope term. I'll explain you in just some while. Don't worry. I'm just trying to give you some basics to it. So supposedly I tell you Y is my consumption. And consumption is dependent on income. If you have more income, you will consume more. If you have less income, you will consume less. So X is my income. I can write this then as consumption is equal to beta naught plus beta 1 income. Do not get confused. This is my income Y, okay? Income is represented by Y in macroeconomics. So then I'm saying consumption is equal to beta naught plus beta 1 income. This is an econometric way of writing the model. Your aim is to estimate beta naught and beta 1 so that you can give it a mathematical form. Your aim is to give me an equation like this, that C is equal to minus 50 plus 0.8y, something like this. When you give me this mathematical form, that is econometrics. So now in mathematical form, we usually start with a linear equation, and mostly what is there in your syllabus is this linear relation. There's just one chapter which is going to talk about different functional forms, in which we are going to understand what are the different ways of writing this relationship. However, whenever you have to estimate, mostly you will see linear form coming up. I'll show you different cases, don't worry. Okay, so now whatever comes here, whatever is a function of the other thing, this is your dependent variable. The thing that comes here, this variable, is called the independent variable. The independent variable is also called explanatory variable because it is self-explanatory. You don't have to explain that. So independent variable, just remember it like that. Independent variable is called explanatory variable because it is self-explanatory. The dependent variable is something that you have to explain. So it's an explain variable that you have to explain. It's dependent, but independent is explanatory. Now, I can also try and give a graph for this. So as I just mentioned, and we will see how to estimate that whenever you talk about any equation which is of this form, you can go back and see in maths also, whenever we would write an equation, and I discussed this yesterday in the microeconomics lecture also, that usually my equation is written in the form of y is equal to mx plus c, where m is the slope, x, c is the intercept. Any equation, any linear equation is of the form y is equal to mx plus c. M is the slope, c is the intercept, x is the independent variable, and y is the dependent variable. This is the exact form in which we have written our relationship. So let's write this down. C is equal to beta naught plus beta 1 income. Let's compare this. So income is my independent variable. Whatever is the independent variable should come on the x-axis always. Consumption is the dependent variable. Whatever is the dependent variable should always come on the y-axis. Then whatever comes with the independent variable becomes the slope. See, this becomes the slope. So beta 1 is the slope and this becomes the intercept. So beta naught is the intercept. So I'm just trying to write this relationship here. Beta naught for my equation is the slope and beta 1, is the intercept, and beta 1 is the slope. Now, as I just mentioned, Some books will write the equation in the form beta 1 plus beta 2y, which is okay. You just have to use your basic concept. Whatever comes with the independent variable becomes the slope. Whatever is this separate term becomes the intercept. And this is how I will draw my line. What is slope? Slope is nothing but perpendicular by base, right? So perpendicular by base, that is the value of beta naught or beta 2. Now, once you have given this model, I just want to highlight something here before we go ahead, that a lot of times the relationship between your dependent and independent variable is not complete. There is some disturbance term. We will see that, right? So, for example, let's say I will take back my example and let's say that I just wrote consumption as a function of income. If I have to go ahead and draw this relationship, I will get C is, supposedly I get an equation out of it, which says C is equal to minus 50 plus 0.9y. And now I ask you, what happens for different values of y? And you tell me that, you know what, when y is 100, C is going to be minus 50 plus 0.9 into 100, which is going to be minus 50 plus 90, which is going to be 40. So your consumption will be 40 when your income is 100. And then I give you different values, okay? So I ask you what happens when your income, let's say, is 200. And you give me some value that, you know, if income is 200, I will put back in this equation. So minus 50 plus 0.9 into 200. So I will get minus 50 plus 180, which will be 130. This will be your consumption. So well enough. But now, if I write my relationship as this, then I am actually stating that, you know, income is solely able to explain consumption. There is no other factor that is required for anybody to explain consumption. Income is enough to explain whatever changes are taking place in consumption. So ideally, when your consumption increased from 40 to 130, it was solely because your income increased. Anytime that your consumption is increased, the reason is solely increases in income. But that may not be the case. Supposedly, my great-grandfather had left some wealth for me, had left some property for me. And today, I get to know that, you know, it is on my name. I've got a good property on my name today. My consumption will instantaneously increase. But that is something which this equation is not taking care of. Alternatively, let's say that, you know, all of a sudden, the momentum in the economy is very bad. My FDs are not giving me any return. I'm getting very poor return on bonds. I'm getting very bad return on stock market. So I decide, I no more want to save so much. I want to increase my consumption. So when my income increases, usually I used to increase from 40 to 130 when my income increased from 100 to 200. But now, the moment my income will increase, I want to just, you know, consume all of my income because the momentum in the economy is bad. The stock market is not performing well. FDs are not giving any good return. Other things are not working out well for me. So this means that there are certain factors that are not included as part of this equation, but they also affect my consumption. All those small factors that affect your consumption, not majorly, but they affect your consumption, have to be taken care of. And that is where I introduce a term which is known as an error term. So ideally, I am saying that because my consumption may follow some random path, maybe because of the factors that I did not take into the model, and those factors are accounted here in the error term, that is why I will not be able to specify an exact relationship, but rather I will specify a relationship which is a bit here there. So, my relationship will give you, will predict consumption for you accurately, but not exactly. What does that mean? It means that supposedly, I had given you my income level of 2011, 12, 13, 14, 15, 16, 17, 18. I gave you different income levels. And for each year, I gave you my level of consumption. Based on this data, you gave me an equation which is this. Consumption is equal to minus 60 plus 0.8y. Now, I ask you that in 2019, my income is $5,000. I ask you, predict my consumption. You just found out this relationship. You're going to predict that consumption for me. You put this y back here. So you get my consumption as minus 60 plus 0.8 into 5,000. This is going to be minus 60 plus 4,000. This is going to be 3940. Just see if I've done the mathematics correctly. So this is going to be 3940. So you end up telling me that, what? I have predicted your consumption of 2019. In 2019, if your income is $5,000, then your consumption will be $3940. Now, 2019 actually comes up and I start consuming. And after I start consuming, my actual consumption comes out to be 3,800. I didn't consume this. I consumed 3,800, which means you predicted a value for me. That value was close enough to my actual consumption, but that value was not exact. The difference between what you predicted 3940, and what it actually came, that difference is your error term. That you predicted something which was not exact. And this will always be the case. You cannot have a perfectly fit model. You will always make some errors, right? Because you did not take into account other factors like my preferences, like my thought process, like my psychological things. You just made a model based on my income level. So that is exactly what is going to happen. This is the line you predicted. This line is what you predicted for me, which was this supposedly. No, we wrote another line, right? Which was C is equal to minus 60 plus 0.80y. You predicted this line for me. So according to this line, I'll make this plus 60 for now. The intercept is 60 and the slope of the line is 0.8. You predicted this line for me. Now, you predicted that somewhere here, when my income is 5,000, my consumption will be 3,940. But my actual consumption came out to be 3,800. This gap, this is the error term of 140. what you predicted from your line and what my actual consumption was. My actual consumption could have been 4,000 when you predicted 3,940. So error could have been positive. And error could have been positive, or error could have been negative. So both the things can happen, right? So these are positive errors, negative errors, positive errors, negative errors, and so on. Now, this is just an example. You can go through the lecture notes later on. So this is what you're going to predict. This is a relationship that was predicted. I think so. This is on the consumption data set only. And this tells me that consumption is minus 299 plus 0.72 times income. That's the relationship that was predicted. And then, for some level of income, if I give you different values of income, you can give me different values of consumption. So if your income in the economy was this much, the consumption of the economy will be this much. So you can do that. And then supposedly, this is doing exactly what I just explained. Suppose for 2006, you predicted that the consumption of people will be 7,870 when income level in the economy will be this much. The actual consumption of people may or may not come out to this number. So if it comes more than this number, you're making an error. If it comes out less than this number, you're making an error. So sometimes the actual number of consumption and what you predict will be different, and that gap will be your error term. So you can go through these lecture notes. And finally, you can also go ahead and help the government in the policy making process with respect to that. So every time the government tells you that, what, tell me, if I want to have my people consuming 4,000, what should be the level of income? So you will put 4,000 in the equation and tell the government that, if the level of income is this much, this is the consumption of the people. Okay, so this is all about the first basics of econometrics, where I wanted to explain you, one, what is econometrics? Two, how do you write hypothesis statements? Three, how do you go through the 8 steps of econometrics? Fourth, how do you make a linear equation? And how do you account for the error terms? To do all of the econometrics, we would be requiring some amount of hypothesis testing. This is also covered as part of the basic videos that would be shared with you on statistics. But I would also be covering this in my live lectures. All right. So having stated that, I am now going to begin with the nature of the regression analysis. So, I'm going to go ahead and begin with a classic example of what was given by Francis Galton. So maybe you have also seen this in your day-to-day life, but he wrote this very famous paper, and what he saw was that supposedly I take two parents. One is tall parents and the other are short parents. Then what he found out is that parents who are tall will have a tall kid, and parents who are short will have a shorter kid. Makes sense, obviously. If my parents have good height, I'm going to have good height. If my parents don't have good height, heredity continues and I may not have a good height. But what he also found out that these children, this child, his height would be a little lesser than his parents' height if they are tall enough. And this child will be a little taller than his parents if his parents are short enough. So the gap between children, these two children's height, will be lower. That's the paper he wrote. We'll see what it means econometrically, but that is what he wrote. So, he said that tall parents are going to have tall children and short parents are going to have short children. But the average height of children born of parents of any given height tend to move towards the average height of the population as a whole. So for example, and that is why I just told you that the gap is reducing. So for example, the height of the parent was 6'1", and let's say the mother was 5'10". And let's say here, this was 5'2", and let's say this was 5. And now let's say that if I take the average of the entire population of this country, the average height is 5'5", supposedly. Then this paper said that the height of this child will definitely be more than 5'5", but it will be closer to 5'5". It will tend to move towards 5'5". This child height will also be closer to 5'5", but it will be definitely lower than 5'5". So maybe this child will have a height of 5'3", closer to 5'5" as compared to the parents. And maybe this child will have a height of 5'8". So he's tall, definitely, because he's born to tall parents. He's comparatively short because he's born to short parents. But you see that these two heights are tending to move closer to the average height of 5'5". When he wrote this paper, that is what and where we gave birth to econometrics. So, this word regress, and by regress we mean to move to a particular direction, actually came from his paper. So let's see a numerical and how things happen in this scenario. So now what I'm going to do is I'm going to give you different examples first, and then I'm going to jump to the mathematical part. This is a classic example of what I just told you. So I am taking my inflation rate here, and I'm taking my unemployment rate here. And what we know, what labor economists have shown us, and this is, by the way, you would have guessed by now, the Phillips curve. Again, a part of macroeconomics. So I'm just taking examples from economics, but because, it is going to help you once you have done the entire course. When you will revisit that, econometrics after that, you would be able to associate it and say, yes, this is a part of the Phillips curve. So this negative relationship of the Phillips curve can be mathematically shown in econometrics. Similarly, what we have to understand is the difference between statistical and deterministic relationship. Now, very, very, very important, because a lot of people tend to get confused between the two. When we talk about statistical relationship, we deal with random variables. Now, if someone may ask, what is a random variable? A random variable is anything which follows randomness. What follows randomness? Anything that has a probability distribution associated with it. Let's see how. Supposedly, I talk about tossing a coin. When I toss a coin, it may give head or it may give you tail. So this event is a random event. So if I say X is tossing a coin, you may get head, head, tail, head. So this is coming randomly. So because it is coming randomly, it has probability associated to it. That, okay, the probability of head will be half. The probability of head is half. The probability of tail is half, and so on. What else is random? Random is your petrol in a car. So, I drive a car every day to office. And now I want to, ask you how much petrol is there in my car in any particular day. So on Monday, you tell me that this is 40 liters. On Tuesday, you tell me it is petrol left is 34 liters. On Wednesday, petrol left is something else. And how much petrol would be left would be dependent on what? It would be dependent on how many distance I covered. So it is going to follow a random path depending on what distance I covered on a particular day. So statistical relationships basically deal with random variables. Deterministic relationships, on the other hand, also deal with variables, but the variables are non-random in nature. They're fixed variables. They're not random in nature. I know their values. Now, for most of our part, whenever we are going to deal with things, I am going to go ahead and deal with the random variables for now. So, for example, let's say that I want to talk about crop yield. And I tell you that crop yield is a function of temperature, rainfall, sunshine, fertilizer, etc. This relationship is a statistical relationship. Why? Because although my crop yield depends on temperature, rainfall, sunshine, fertilizer, etc., these are not enough. And I just introduced you to the concept of the error term. Even if I've taken 4 main factors that may affect my crop yield, there may be some small factor that I have not taken. And because I haven't taken all the factors into consideration, I will be able to predict crop yield, but there will be some randomness involved. Right? Similarly was the example of consumption and income. So I may tell you that my consumption is a function of my income. My consumption is a function of my preferences. My consumption is a function of the wealth of my parents. And, now I may give you a model on this and you may be able to predict consumption for me. So is this a complete relationship? The answer is still no. There are still some factors that you may not have taken into consideration. For example, let's say consumption depends on my peer pressure. If my friends consume more, if my friends go to more cafes, then I will save less. I will also consume more. So because I cannot take all the factors into consideration, there will always be some randomness in the model. That randomness will be given by the error term. So whatever, models you're going to deal with in econometrics will always be statistical in nature. What is a deterministic relationship, if someone may ask then? What is something which is non-random in nature? How do I know it is non-random? Anything which is completely defined. For example, equations in physics. Force is equal to K into M1, M2 by R square, where M1, M2 are the masses. Something which is completely defined. For example, the formula for gravity, the formula for force. We used to write, I think so, I'm not very sure, force is equal to mass into acceleration, right? So formula is like this. These are deterministic in nature. There is no other factor that is going to define force. These are the only factors that are going to define force. In that sense, these relationships become deterministic. You're not interested in these relationships at all as part of econometrics. You're only interested in statistical relationships as part of econometrics. Okay, one last thing which a lot of people get confused too before we go to the mathematical parts of it is regression versus causation. See, as the word suggests, causation is if something causes something. Regression is more of a mathematical relationship. Sometimes I can establish a relationship upon something, but it may not be a causation relationship. The cause may not be defined. So, for example, let's say that I find out the relationship between crop yield and rainfall. Now, there are two things. One is the regression equation that we just formed. The other thing that you can do is just find out the correlation. Now, again, refer to the basic videos of statistics. Whenever I mention this, when you go back, you get these videos of statistics, go through them. In correlation, there are various correlationships. One is Spearman correlation, rank correlation, Pearson correlation. So you have to ideally just understand what is correlationship for now. Correlationship is the relationship which is both-sided. So if I say that the correlationship between variable A and B is 0.90, then it is a dual way relationship. A and B move in the same direction with 90% relation. So in this case, I know that whenever I have to plot correlation, ideally, I can say something like this. So I can say if my correlation is 1 to 0 to -1. A 1 correlationship is perfectly positive correlation. The two move in the same direction, but perfectly same. If one doubles, the other also doubles, something like that. -1 is perfectly negatively correlated. Zero is not correlated. As you keep moving towards 1, the correlation is stronger. If you give me that the correlation is 0.1 between two variables and the correlation is 0.90 between two variables, these two variables are much strongly associated with each other. Similarly here, they are much strongly negatively associated with each other as compared to this. So as you go towards this, there is a stronger negative correlation. Now, supposedly, I tell you that there is a correlation between crop and rainfall, and the correlation is 0.90. Then this doesn't give you the causation. This actually tells you that the two move in the same direction. As rainfall increases, crop yield increases. As crop yield increases, rainfall increases. But my economic sense tells me that rainfall cannot be a function of crop yield, right? Rainfall will not depend on anything except the process of evaporation. But crop yield is a function of rainfall. So that is where causation comes into picture. That is where I go ahead and I apply my theories. This is just telling me that the two move in the same direction. But I have to go a step ahead and tell that, although the two move in the same direction, rainfall cannot depend on crop yield. Crop yield will depend on rainfall. Prices will not depend on quantity demanded. Quantity demanded will depend on prices, right? So that is something where you will use your economic sense to explain things better. So I know that there is a positive relationship between smoking and lung cancer, but lung cancer doesn't cause smoking. Smoking causes lung cancer, right? So the correlation coefficient measures the strength of the linear association. It just tells you whether two things are strongly positively related, strongly negatively related, related or not related. But you have to remember this. I will come back to this point in one of the chapters. Only linear relationship. Supposedly, something has a quadratic relationship. Suppose I tell you y is equal to x square. Something like this. Then this equation, if you find its correlation, it will give you a correlation of 0. Doesn't mean there is no correlation. Y is associated with x, but there is no linear correlation. So correlation coefficient is only capable of giving you the strength of linear relationship. But you know, if you have to go a step ahead, if you have to understand what is affecting what, if you have to understand and predict the values, that you know, if smoking increases, what are the chances of lung cancer increasing? By how much will lung cancer increase? If you have to calculate all of that, you have to move a step ahead to regression. So regression is one step ahead of correlation. So this is some of the terminology. A lot of students get confused while they're going for the terminologies. The dependent variable is also called the explained variable. Why? Because you have to explain that. That has to be explained by the independent variables. You have to find a way to explain it. So it is explained variable. The independent variables are called the explanatory variables. They're self-explanatory. You don't have to explain them. The independent variables are the predictors. They predict it for you. The dependent variable is the predictand, something that has to be predicted. Again, the explanatory variable or independent variable are called regressor. You're using them for the purpose of regressing. But what has to be predicted is the regressand or the response. The independent variables are the stimulus. The independent variables are exogenous. They're not defined inside the model. They were defined outside the model. You just picked up their values and come. The dependent variable is defined within the model, because that is what you're trying to find out. You're finding out the value of the consumption based on your income. So consumption is defined within the model. You're trying to find out its value within the model. So consumption becomes the endogenous variable. The independent variable is also known as covariate. The dependent variable is called outcome. The independent variable is called control variable. It is controlling the movement of the dependent variable. So the moment this changes, its movement changes. So the independent variable is control variable, something that is controlling. The dependent variable is the controlled variable. It is getting controlled. So it's the controlled variable. So these are the various terms that you have to take in mind. Just one more thing which is important in terms of terminology. Anything which is random is called stochastic. Anything which is non-random is called non-stochastic. My x's are non-stochastic in nature. By x's, I mean my independent variable. My independent variables are non-stochastic. There are three main types of data to work with. To begin with, we are only going to deal with my cross-sectional data. Time series is pooled is definitely out of scope for your purpose. Time series is not explained too much in detail. very short, very short analysis of time series data would be done. What is time series data? Time series data is something where I talk about one variable over a period of time. So if I take the sales of a company from 2000 to 2020, that is time series data. What is cross-sectional data? In one period, but many variables. So if I ask, what is the sale of TV? If I talk about an electronic, company. So what is the sales of TV, sales of, let's say, fridge, sales of refrigerator, washing machine, sales of laptops, etc. But only in one period, only in 2010 or only in 2011, that's cross-sectional. So one period, many variables, cross-sectional. One variable, many periods, time series. Many variables, many time periods, pooled. So pooled is time series plus cross-sectional. So if I ask, what is the sales of TV, fridge, washing machine, laptops, etc. in 2011, 12, 13, 14, and so on. So many periods, many variables, that is your pool data. There are four main scales that are important. This is usually a question that comes in papers like SAU, papers like University of Hyderabad, papers like Jamia, JNU sometimes, etc. So, here we are trying to talk about what is the, and it may come in the papers like IIT also. So there are four main scales that you have to understand. Scales of variables of measurement: the ratio scale, interval scale, ordinal scale, and nominal scale. I'll begin with the ratio scale. Ratio scale is whenever we have to compare two things, whenever we have to find ratio of something. So for example, if I have to ask what happened to the GDP of 2020 as compared to the GDP of 2019, when I compare, when I ask you, what's the growth rate of the GDP, that's my ratio scale. So supposedly I ask you, how much is India earning as compared to US, or how much is US income as compared to India? Are they earning double of what we are earning? That is where we have to talk about the ratio scale. So the ratio scale is meaningful to find out the, what is how much times the other. It's meaningful for the purpose of the comparisons. The other scale which is important is called the interval scale. The interval scale will satisfy many properties of the ratio scale, but the interval scale is something which is not meaningful for the purpose of comparison. So, for example, I tell you that, the temperature in Delhi is 49 degree. The temperature in Bangalore is, let's say, 28 degrees Celsius today. So, it's important to understand how much is the difference between the temperature of the two places. That is going to make sense to me. So, I understand that Delhi minus Bangalore, this interval is helpful to me. But I will, this thing will not be helpful to me when I will say that Delhi's temperature is twice of Bangalore temperature, right? You don't write comparisons of the temperature, but you are interested in understanding that, the difference in the temperature is this much. So interval scale is when you are interested in understanding the difference, but you're not interested in understanding by how much. For example, I might be interested in understanding that I have scored 20 marks more in maths as compared to science. But I may not be interested in understanding that I might not be interested in doing that my math score is double my science score, is 1.2 times my science score. That is not something I want to do. So in that sense, I don't want to go ahead and do that comparison, but I want to find out that distance. I want to find out that gap between the two things. That is interval scale. The third scale is ordinal scale. Ordinal scale is where, and by the way, this is something which is, I referred to this in our micro lecture also. Ordinality is a concept which is hugely used in the utility concepts. So the ideal example from economics for ordinal scale would be utility. What is ordinal scale? Ordinal scale is where I want to rank things out. So I want to say that Delhi's temperature is more than Bangalore's temperature, but I don't want to find the difference. So in ratio scale, I wanted to find the difference between the GDP. I want to also find out what is double of what. I also want to find out the ranking. I want to do everything in the ratio scale. In interval scale, I want to find out the difference between Delhi and Bangalore temperature, but I don't want to find out if something is double the other or not. I don't want to find out that ratio. In the ordinal scale, I'm not even interested in the gap. Just I'm interested in the ranking. So I'm interested in understanding that person A is rich, second is middle class, third is poor. But I'm not asking whether rich income is what, poor income is what, and middle class income is what. I understand that I'm going to prefer bundle A over bundle B. A's utility is more than bundle B's utility, but I don't want to know the gap between the utilities of bundle A and B. That is not going to make sense to me. So ordinal scale is where you want to talk about the ordering. You want to talk about the ranking, that bundle A is better than bundle B, but you don't want to talk about the difference. You don't want to give a mathematical form to it. And finally, what we have is the nominal scale. The nominal scale is the lowest of all. So ideally, if I have to write these things in the ascending order, it will be nominal is the base. Then if I give ranking to it, it becomes ordinal. If I add the interval gaps to it, it becomes interval. And finally, if I add a ratio to it, comparison to it, it becomes ratio. So nominal scale is having none of the features. It's just any variable is a nominal scale variable, like gender, which is male, female, like marital status, which is married, unmarried, divorced, separated. I don't want to, so when I say gender, male or female, I don't want to talk about ranking. I don't want to talk about interval. I don't want to talk about comparisons. I just want to talk about variable which takes two values. Similarly, marital status, married, unmarried, single, divorced, etc. I'm not talking about ranking, gap. I'm not talking about ratios. I'm only talking about variables. That is it. So these are just categorical variables, and that is it. So this is important from exam point of view also. Okay, we'll take a short 5-minute break, and finally I will come to some mathematical concepts then. Okay, I will now start with the two variable regression analysis. To begin with, you have to try and understand this mathematically. So let's start with an example. See, I am taking two variables, X and Y. My X represents the income of family. And Y represents the consumption. This is very, very important. So you have to, see this from the very beginning. If you don't understand this example well, the base is not formed well, because this is going to be the base of multiple linear regression model, dummy variable, functional form, whatever you want to do. So understand this example really well. Now, I have this as 80 as the income level. When income is 80, the family consumption varies. There are various families. Some family, when their income level is 80, consume 55. Some families, when their income level is 80, consume 60 out of 80. Some families consume huge income out of huge income level and save very less. So they consume 75. So now understand that the behavior of people is differing, even though the income level is the same. So what we are trying to do, we are saying that the income level of people is 80. And when the income level of people is 80, the consumption varies. Income level, all these people have the same income level. But when the income level is 80, one family just consumed 55. The other family consumed 60. The other family consumed 65. The other family consumed 70. And the other family consumed 75. Given the fact that all of them have the same income level, which is 80. Now, let's take other example, income level as 100. So there are some families whose income level is 100 per week. If their income level is 100 per week, one of the families still consumed 65 out of 100. So 65 out of 100. The other family consumed 70 when their income was 100. The other family consumed 74, a little lower than 75, right? So the other family consumed 80. And then you had 85 and 88. Conditional on the fact, I'm again and again repeating, conditional on the fact that the income level is 100. Let's go ahead and see it further. Supposedly the income level is 120. Again, one family had 79 out of 120. They consumed 79 and so on. Similarly, I can do it for 140, for 160 and so on. So these are the figures that are given to me. Now, what I'm going to do is I'm going to find something which is known as conditional mean. Let's understand the concept of conditional mean first. Conditional mean, as the word suggests, is conditional on a given level of income. So I am asking the question, given that income level is 80, what is the average? This is the sign for expectation, right? What is the expectation consumption? What is expectational consumption? So given that the income level is 80, how much of consumption should one do? That is the question that I'm asking here. So now it's simple. Given that the income level is 80, there were only 1, 2, 3, 4, 5 families whose income level was 80. What is the average income then? Average consumption then? it would be 75 plus 70 plus 65 plus 60 plus 55 divided by 5. You give a number for that, so the number becomes 65. So I, go ahead and I am going to mark this as 65. So 65 tells me that within the families which have an income of 80, only within those families that have an income level of 80, the average consumption is 65. On an average, families consume 65. Similarly, if I ask you, what is the average consumption given that the income level is 100? So you're going to find average, but only within the families that have an income of 100. What are those families? These families. These families are the families that have income level of 100. So given that all of these families have income level of 100, what is their average? So you are going to say 65 plus 70 plus 74 plus 80. I'm just averaging this part, okay? Plus 85 plus 88 divided by 6. There are 6 families that have income level of 100. You find an average of that, and the average comes down to 77. So that is my average. Somewhere over here. I repeat the same process of finding the conditional means. So supposedly, given that the income level is 120, what is the average? Given that the income level is 140, what is the average consumption? So you get some averages here. You join this averages, conditional averages, and what you get is called the linear regression line. So let's see what we have done here. For all the families that had an income of 80, I plotted those incomes. I found out the conditional mean. So this is finding the average of the consumption given the income level equal to 80. Finding average of the consumption given income level equal to 100. Finding average of consumption given income level equal to 120. This is finding average only for the families that had income level of 100, only for the families that had income level of 80, only for the families that had income level of 120. You keep plotting those conditional means. You join those conditional means together. That gives you the regression line. Okay. So ideally, if this is what my regression line is, the equation for the regression line should look something like this. Why should it look something like this? Because what I am doing here, I have my x's given to me. My x was 80. For these x's, I found out the conditional mean. So my conditional mean was conditioned on the fact that x was 80. It was function of x being 80. When I found out the conditional consumption, it was dependent on income being 80. In the next case, when I found out the conditional mean, it was dependent on income being 100. In the next case, when I found out the conditional mean, it was dependent on income being 120 and so on. I joined all these points together and this gave me the regression line. So regression line is not y is equal to beta 1 plus beta 2 xi. Regression line is a relationship between conditional mean conditional on the values of the independent variable. And it has some intercept and it has some slope. So I write a usual linear line, beta 1 plus beta 2 xi. That is your regression line. So let's go ahead and look at that. This line is called the population regression line. This is, how do we achieve this? This is achieved by joining the conditional mean values together. The population regression line is also known as the population regression curve. And how do you do that? It is the locus of the conditional means of the dependent variable for the fixed value of the explanatory variable. So very important, whenever you are plotting the regression line, the way to make the regression line is this, E of y given xi. You're joining all these conditional means together is equal to beta 1 plus beta 2 xi. But this is for the population. Now, a slight note on what is population. See, population is whenever you take all the families and you find accordingly. If sometimes you do not have access to the entire data, what you do is instead of finding the regression for the population, you find a corresponding line for the sample. So supposedly, instead of these 60 families that were given to me, so these are 60 families in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. These are the consumption given for 60 families. Supposedly, my population was not at disposal. I didn't have enough time to collect data of all the 60 families. I ended up collecting data of only 10 families or of only 15 families. Then the line that I will get from that will be called a sample regression function. That would be where you would be using some families, a subset of the families, a sample to estimate information about the population. So we will see that. Let's see it. So let's go back at this diagram. This is my x. X is my independent variable. Whatever comes on the x-axis is my independent variable. For me, my independent variable is the income. Consumption depends on income. So consumption comes on the y-axis. These are all the conditional means. I am joining the conditional means together to get my population regression function. So I'm joining all my E, Y given xi. Finally, something that I will show you as we go ahead, I want to talk about distribution. By distribution, I mean that if I find out now, what is a normal distribution, first of all? This is part of the basic videos of statistics. Please refer to those. In that, I have explained in detail what is a bell-shaped function. But what is normal distribution? A normal distribution is something which is one symmetrical. What do I mean by symmetrical? It means that if I find out the mean, which is equal to median, which is equal to mode, if I find mean, median, mode, which are all three are equal in our case, then 50% of the data will lie here and exactly 50% of the data will lie here. It's a symmetrical distribution. It's a bell-shaped distribution. As against this, what are the other cases that can happen? Your data can be skewed. So for example, your data can look something like this, or your data can look something like this. But we don't have such kind of data. Our data is a bell-shaped, pretty good data to work with, which is a symmetrical data to work with. And what we are saying is that, so now in our diagram, I just plotted these conditional means, right? So along this mean value, your data is normally distributed. Similarly, when the mean is this, along this mean, the data is normally distributed. When the conditional mean is this, the data is normally distributed. So at any point of time, this is just for simplicity, we are assuming that y values are distributed symmetrically around their conditional means. 50% of the y values are above the conditional mean, 50% of the y values are below the conditional mean. And this is something which we just saw also, right? So I'll give you, I'll take you back to my diagram. Just have a look at it. 2 values are above this, 2 values are below this. 3 values are above this, 3 values are below this. 2 values are above this, 2 values are below this. So more or less, there is a symmetry. If you look at the values also, you will see that they're, symmetrical in nature. So that ways we're assuming that they follow a bell shape. They are symmetrically distributed. More on normal distribution in chapter 3, but just for now, you understand that you have symmetrical distribution unlike a skewed distribution. Okay. So finally, the equation that we wrote is that my expectational mean, conditional mean, is a function of x's. So my population regression function that I have is expected value of y given xi is a function of my x's, or expectation of y given xi, the conditional mean, is beta 1 plus beta 2 xi. So this is how you can write your population regression function. Now, the question that then arises is, how do you interpret this function? I've got this function in hand. How did I find this function? I simply just joined the conditional means together. And the moment I joined the conditional means together, I got an intercept. I got a slope. And if I got that, I got my regression function with me. But how do I interpret that? So there are two main things for the purpose of interpretation. This is called the intercept term. And this is called the slope term. So, supposedly, I tell you E of y, I'll give you in terms. So, expected value of consumption given income is equal to 80 is some value, was 100. Then E of consumption given y is equal to 100 was 120. I joined these points together. I got a line out of it. And my line looks like this. E of y consumption given income is equal to minus 80 plus 0.9 times income. The question is, how do you interpret this? So, interpretation for intercept term. The intercept term suggests that when you put this y equal to 0, supposedly I put y equal to 0, income as 0, what do I get? I get E of C given y is equal to minus 80. So the intercept term tells you that when income is 0, on an average, Why am I writing on an average? Because we just said that this is conditional mean. And by definition, mean is average. So when my income is 0, on an average, the consumption is minus 80. Now, supposedly, I have to interpret the slope term. So I'm saying E of C given Y is equal to minus 50, minus 80 plus 0.9Y. The interpretation of the slope term. So how do we interpret that? See, the slope term, because always it is perpendicular by base, and it tells you how the y variable changes when the x variable changes. So it tells you how the average consumption changes when the income changes. So how do we interpret the slope term? The slope term is interpreted as when income increases by 1 unit, on an average, consumption increases by 0.9 units. This is important, on an average. This is the interpretation of your equation. So slope term tells you when the explanatory variable increases by 1 unit, what happens to the explained variable. Whereas the intercept term tells you when the explanatory variable is 0, what is the value of the explained variable. So, let's take few more examples, and let's do one more case before I go ahead. So supposedly, I am taking the Phillips curve. Please interpret this. So supposedly, your equation looks something like this. Inflation is, or let's talk about unemployment, okay? Unemployment is 0.87 minus 0.2 inflation. Supposedly, this is the equation that I found out. Now, let's interpret both the terms. So, 1, intercept term. So, intercept term tells you when inflation is 0, there is no inflation in the economy. Prices are not increasing at all. When inflation is 0, on an average, unemployment is 0.87%. Second, or I will just use units for now, 0.87 units. Second, what is the interpretation of the slope term? When inflation increases by 1 unit, when I increase inflation by 1 unit, then on an average, unemployment, please, this is important, okay? On an average, unemployment decreases by 0.2 units. So every time you will increase inflation, unemployment will decrease by how much? By this. And why have I used the word decrease? Because there is a negative sign here. Beta 2 is being followed by a negative sign. So when this increases, unemployment decreases. Had it been a positive sign, I would have said when this increases, this also increases. Okay. So this is how we explain the intercept term and the slope term. Now, let's talk a bit about linearity. There are two things. One is called linearity in variables. The other is called linearity in parameters. What is linearity in variables, first of all? Linearity in variables means that the variable that you have, that x that you have, should be linear in nature. Linearity in parameters is something we are interested in. Even if we are not linear in variables, we are fine. We want to be linear in parameters. So linearity in parameters is when your beta 1 and beta 2 factors, they are linear. So let's see that. I'll give you an example of it. So supposedly, I give you an equation which is y is equal to beta 1 plus beta 2 x. This is linear in parameter and linear in variable both. Now, I'll give you an equation which is y is equal to beta 1 plus beta 2 x square. The parameters are coming linearly. They are not in square term, they're not reciprocal, they're nothing. But the variable is non-linear, right? It's coming in the square term. Y is equal to beta 1 plus beta 2 1 by x. This is linear in parameter, non-linear in variable. Y is equal to beta 1 plus beta 2 ln x. This is also linear in parameter, non-linear in variable. Supposedly my equation is y is equal to beta 1 plus beta 2 x cube, linear in parameter, non-linear in variables. Supposedly my equation is y is equal to beta 1 plus 1 by beta 2x. Then it is linear in variable. X and y are coming linearly, but non-linear in parameter. This is not coming linearly because this can be rewritten as, So you know, y is equal to beta 1 plus 1 by beta 2x can be rewritten as y is equal to beta 1 plus beta 2 to the power minus 1x. So this becomes non-linear. So you have to understand this is linear in variable but non-linear in parameter. So non-linear in parameter is when parameters don't come linearly. Non-linear in variable is when variables don't come linearly. This is an equation which is linear in parameter and variables both. This is an equation which is linear in parameter but non-linear in variable. Do you see that? This is y is equal to beta 1 plus beta 2x plus beta 3x square. So this is linear in parameter but non-linear in variable. This equation is linear in parameter but non-linear in variable. This equation is linear in parameter but non-linear in variable. From now onwards, whenever I'm going to talk about linearity, I am always talking about linearity in parameters. So if I say this equation is linear, assume I'm talking about linearity in parameters, irrespective of what happens to linearity of the variables. You're not interested in that at all. So linearity in explanatory variables may or may not be true, but I'm always talking about linearity in parameters. That is my aim. Let's talk about this now. This table is going to explain this thing in much more detail. If something is linear in variable and linear in parameter, definitely it is a linear model. If something is not linear in variable, but still linear in parameter, why betas are coming linearly, then also it is a linear model. I can work with that. If something is not linear in parameters, it is non-linear. Simple. The moment it becomes non-linear in parameters, it's a non-linear model. Simple as that. Only if it is linear in parameters, then it is a linear model, irrespective of what happens with the variables. So I'm not really interested with the variables. Okay, I'll stop here for now. And in the next class, I'm going to introduce this U term in detail to you. And I'm going to do a question based on that from DSC past year. What you have to do for now is the following. Go through this video, understand linearity well, understand how we find out the PRF, and finally, do some basic videos of statistics where I'm explaining what is normal distribution, where I'm explaining what is mean, what is median, what is mode, so that you're clear with the basic statistics concepts.